Everyone, so today we're going to continue talking about firewalling a little bit. We're going to talk about UFW, kind of alluded to that on Monday. So UFW is the so-called uncomplicated firewall. So with IP tables, there's a lot of syntax that you can really mess up, and UFW tries to make the syntax much easier. It uses IP tables underneath it all. So we're going to get into just the basic usage of that. Generally speaking, most of the firewalling things that you'll probably see you can accomplish with UFW, just allowing ports, blocking ports, things like that. But when we get into more complex stuff, and we're going to have some examples of some perhaps complex stuff that we will do with IP tables later on, which we're going to look at NAT, and we're going to look at kind of tinkering with traffic a little bit, getting it to do some strange things, or very, very controlled things, but very perhaps interesting things a little bit later on. So yeah, UFW again uses IP tables underneath it all. There's a service that's usually running. UFW is actually installed by default on Ubuntu, I believe, but it's disabled. So you would do a UFW enable to actually enable the firewall. But before you do anything, it's probably worth doing the UFW status, and then probably UFW status verbose, and we'll talk about that here in a second. Status says inactive, verbose still says inactive. So again, in order to start things up, let's just look at the UFW service really quick. I think it's just UFW. So we can see if we run this, it gives us something in return, whether it's active or stopped or dead or something like that. We know that UFW is installed in the system and can be configured. So if it, again, as usual, if this didn't say active, we would say something like systemctl start, enable, things like that. Pretty straightforward as usual. Anyway, so to get started with this, we do UFW enable. And it's also, let's do this first really quick before we do anything else. Let's look at what we had left over in IP tables from Monday. Just kind of as an example how IP tables and UFW can perhaps coexist a little bit. Tables L. So right now we have absolutely nothing. The only thing we do have is the except rule on input for SSH, and our default policy is drop. So UFW enable, and we'll just allow that. So firewall is active enabled on system startup. Now if I was to do UFW status, say active, you can see it actually took the rules that we had. Well, I don't think it actually, these rules probably didn't originate from here. These rules, it since we were SSHing into the VM and automatically added those SSH rules. Now if I was to go back and I was to look at IP tables after I had started UFW, you can see there's actually a whole bunch of different chains that have been added by UFW. And one of the things that you can do when you look at IP tables more in depth is you can actually, instead of jumping to a target, so allow, deny, reject, you can jump to different chains. And to kind of compartmentalize everything, UFW actually adds its own chains, and then I believe up in input, what it will do is it will just actually go to each of these chains. So instead of actually adding rules to input, forward, output, it jumps to this chain, processes all the rules there, and jump all the way through that. And that kind of just compartmentalizes all the rules that UFW is working with. If there's other programs that are running, you, the system administrator, are manually adding things to IP tables, this would kind of just keep all the UFW stuff separate from all of your stuff. And you can see up at the very top of input, we actually still do have that same SSH rule from before. But I think if we go down to, let's see, after input, yeah, so the input one right here, there's another SSH rule, and that's the SSH rule that actually was added by UFW when we started up again because it sensed that we were SSHing in. So I think by default, UFW will also change the default policy to drop. If you recall from before, we had a policy, a default of drop on input, but we had a policy of accept by default on forward. And if we go down to our new output, we can see that the policy on forward has been changed to drop. So it would probably be safe to assume that UFW is going to, by default, drop input and forward. So there's that. So as for the syntax, when we were doing something, I probably have it in my history here. Deport. So this is how we would allow SSH. Kind of complicated. I'll move that up here. IP tape. So that's how we would go about allowing SSH. Slightly complex syntax. You might screw it up. I know I screw it up all the time. With UFW, it's of course a lot simpler. You could say UFW allow, and then say a port. So let's just allow inbound 80. And the things to note about that is when you do that, it does a lot of things in kind of in the background that you might not sense at first. So if I do UFW status, we see we have 80, and we not only have it on IPv4, we have it on IPv6, and that's something that I don't think IP tables would do by default, is both the IPv4 rules and the IPv6, something to keep in mind. The other thing that's not apparent here when we're looking at the UFW status output is that this rule here is actually for both TCP and UDP. We could actually control that a little bit more if we wanted to. When we were saying allow 80, we could say /TCP, and that would only allow 80 on TCP. And we can see it's specifically TCP here when we go to look at it. Very simple to delete rules too. You just say basically the same way. You just say UFW delete allow 80. And then if you do status, you can see that we're just left with the rules that we had before that. So yeah. So we have allow, we can specify a port. If we want to specify the port and the protocol, we could say port/protocol. So we could say 80, we could say 80/TCP, 80/UDP if we wanted to. And again, remember it implicitly defaults to UDP or TCP and UDP. The other interesting thing that we can do is we can actually say a service here. So one interesting file that we haven't talked about on Linux yet is the services file, and that file actually contains a basically a map of a service name and then the port and the protocol that that service actually works on. So if I was to say SSH, basically UFW would go through this services file, it would look for SSH, and it would replace SSH with this port and protocol specification. So if you don't recall offhand, if you don't really care what the port and the protocol is, you can just say the name of the service, and it will just fill it in by default. So let's look at Telnet as a good example, 23 TCP. So if I was to just say UFW allow Telnet, it just automatically looks up the service in that etc services file, and you can see now we're allowing port 23. So pretty straightforward. You can do the exact same rules with deny, so deny a particular port, deny a particular service, and we won't get into that very much since the policy right now is by default deny. Not too much sense in specifically denying things more, denying them even more. So another thing that we can do, just like we did with IP tables, is turn logging on. The difference here being that we don't really control what we're logging. We just kind of log everything. So we would just say UFW logging on, say logging enabled, and I'm not exactly sure where it goes to. I've seen it in varlog UFW before, Let's take a look at this, and it probably is in the syslog, just like our IP tables logging rules. So we'll try and connect to it, and look at our syslog. And yeah, we can see we have a bunch of these block lines in our log file here. So it says UFW blocks. Block, it says what interface. Again, all of the same things that we saw from IP tables before. It just has this nice UFW block on, and that will happen for any block, not just the ones that we specified. So we manually specified what we wanted to log with IP tables. With UFW, we just get everything. And I mean, we could simulate this behavior with IP tables as well. We could just say IP tables a input, literally jump straight to log, and that would log everything right away. And that's probably what UFW is actually doing in the background. We can take a look at that and figure out what it's trying to do. We could say IP tables L. And we can see right here is our logging rule. And basically, if we were to look through it more and try and find where this UFW logging deny would be, I believe it would be they're jumping to a chain, they're jumping to another chain, and then they're finally ending up there. So I won't look into it very much more in depth than that. And they've actually configured that prefix that we looked at before. So that's why they're seeing that right there. They configured the prefix. They configured a lot of the other features of logging, so you don't get a bunch of log spam if somebody is port scanning you or doing things like that. But you'll still get enough information to make good decisions and figure out what's going on with your machine. So yeah, that's UFW. I think that's basically all I wanted to talk about. Okay, and there's one more thing. UFW allow from IP address. So if I wanted to, let's say we're in our load balanced, this is probably what I'm going to have for the lab, and how we're going to apply this. You can use UFW, you can use IP tables or whatever. But let's say we have our load balanced WordPress setup and everything, and we only want users to be allowed to navigate to the load balancer itself. So what we might do is we might go on the Ubuntu 3 or Ubuntu 2, 3, and 4 and only allow traffic from the, in the case of the Apache host, the 2 and 3, we'd only allow traffic from 1, and from 4, we'd only allow traffic from 2 and 3. So we could do something like this. I'm not in the environment right now, but I'll just show you kind of what I would try and do. I'd say UFW allow 192.168 1.21. That would be Ubuntu 1. I'll move this up here so we can see it better. UFW allow 192.168.221. And I think I could actually elaborate on that a little bit. Okay, I have to say allow from, and that would allow traffic on all ports if I wanted to. But I think I could also say form from. I could also say, I believe, like port 80. I believe I could say that. I might have to say, I might leave off the port and I might just say 80 TCP at the end. I'm not exactly positive on the syntax there, but that's generally how you would go about doing it. I mean, same thing you could do from IP tables. You could say IP tables, A input, P TCP, D port 80. I believe S is the source IP address, 192.168.221, and then jump accept would be the way that you'd go about allowing just inbound on port 80 from that one specific IP address. Again, in an IP tables context at least, we would just leave off that S part to allow from everybody. In UFW, we just say UFW allow 80, and that's how we would just allow that. So yeah, I think that's all I wanted to talk about with UFW now. I think we've covered all of that. Again, just an easier way to work with IP tables. And you could kind of have them coexist and work together. But generally, if we get into the more complex stuff that we're going to talk about next, I kind of suggest to just not do UFW. And if we're doing the more complex stuff, we should pretty much understand how IP tables works anyway, so we can probably just do it. So for this next part, again, I wanted to explore a couple more interesting IP tables, things that we can do. There's actually more tables than what we've looked at. So looking at this diagram here, it's a very good explanation of what's going on. So we had seen 3 tables so far. We'd seen input, forward, and output, and those are the tables that we want to, or that are visible by default, and that's where most of our rules would go. We want to block inbound traffic, we want to block outbound traffic, allow things, deny things. The very typical firewalling rules. But we haven't really talked about forward much yet, and we're going to get into what forward means. But there's 2 tables that are important when we're doing forwarding, and that is pre-routing and post-routing. So in addition to just doing the firewalling stuff, IP tables also does kind of routing stuff. So if we receive a packet that's destined for an IP address that isn't ours, we can actually take that packet and forward it on to another IP address. And one of the things that we're going to need to do in all of that, and it's not necessarily that we need to do this, but it's what's most common, is we're going to need to NAT that traffic through our host. And what that means is, of course, we're going to change the source IP address to be our IP address, so that when we forward on that traffic to another network, it will know that it came from our host on that network. And I'm going to come back to this diagram here in a little bit. But basically, for this example, I've added another client to the IALab network that we have. It's only on mine right now. I might see about adding another one to your guys' network. I don't know how easy that is. But basically what's going to happen is I have another network connected here, and this goes on to Ubuntu One, and then Ubuntu One connects on to our main network here. So what we want to do is kind of the typical, hopefully you're familiar with this kind of NAT, LAN kind of thing. This would be sort of our LAN here, and this would be sort of our WAN over here. So we're going to basically send traffic. We're going to default gateway Ubuntu client to Ubuntu One. Ubuntu client is, I think, 2.100, and Ubuntu One is 2.1. And we're basically going to send our traffic from Ubuntu client to Ubuntu One. And then what we want to do with IP tables and a couple other Linux kernel things is forward that traffic and masquerade it, was the term we use in the Linux environment, masquerade it through Ubuntu One. And again, masquerading in a NAT environment will change the source IP address, and we'll look at, and that's the other thing I want to do here kind of, is look at how all of this is working with TCP dump, and we'll show the packets coming in, we'll show we'll show how to configure IP tables, and then we'll show the packets coming out of Ubuntu One with TCP dump, and we'll show how all of this is working. And hopefully it'll be a good explanation and everything. And I think it's relatively interesting to think about too. So to configure all of this should be relatively straightforward. What we do is we have to turn on a Linux kernel feature, IP forward, and we're going to specifically do it for IPv4. When we're working with forwarding traffic through our host by default, I don't know of any distribution, in fact, that has IP forwarding turned on by default. We have to turn on the actual IP forwarding feature. So again, we can't do that by default. And this is just one of the Linux kernel features that we can kind of tinker with. There's this etc sysctl conf that we're going to look at. Yeah, so we're going to go ahead and do that. So have Ubuntu client. We're not really going to configure that at all. It's just going to be a host. Again, if I look at this output, we can see it's at 200. If I look at Ubuntu One, we have two interfaces, ENS32, ENS34. 32 is on our main network. 34 is our kind of like our more LAN, secondary LAN that we just added that connects us to Ubuntu client. That's 2.1. I'm going to move this. I'm going to rearrange this slightly so I can get to it easier. So let's look at our sysctl really quick. So we have sysctl.conf, and this is where a lot of these directives go. If I look for IP forward, we can see it says uncomment the next line to enable packet forwarding for IP version 4. And sorry if the lighting and everything doesn't work out quite right, but it's unfortunately this color, and I don't think I'll be able to change it. So I'm just going to go with it. Again, fairly straightforward procedure, I think. And as long as you're aware of this one thing and this one thing, I think we should everything should work out all right. So we're just going to uncomment that and say sys. Well, so I guess I did this in the wrong order. So when we change things in this file is loaded on boot. There's also a way to load it with sysctl, but I don't remember offhand how to do that. What we can do is just say sysctl, the command, so there's a sysctl command actually, sysctl net.ipv4, I think, .ip forward equals 1. And that will turn on IP forwarding for our current session, so just right now, and then when we change it in the file and yet see sysctl.conf, that will change it for all of our sessions, and that will be persistent throughout everything. So you definitely want to do it both ways. Excuse me. So yeah, so the first step of turning on IP forwarding, right now, let's go over to Ubuntu client. I only believe I had an IP address, and actually I had the gateway already configured too, so we're good to go. So right now we're gonna come back. We're gonna just do this basic NAT thing. Then we're gonna think about what other features a LAN might have that we're going to look into services to fulfill those features a little bit later on. But right now, of course, I could ping my gateway, but if I was to try and ping anything else, that wouldn't even work right now because we don't. Let's ping 1.1. So let's, as we're doing that, go over here and think about that. So Ubuntu client is going to send its traffic to Ubuntu 1 to be forwarded on, and then once we have everything up and running, Ubuntu 1 should forward that traffic over to 192.168.1.1, which is the pfSense box right here. So it's interesting, I think, to look at the TCP dump output and see if things are actually working. One of the things that we might expect to have functioning right now is, it might happen, I'm not exactly sure what's going on, is the traffic might be flowing through the Ubuntu 1 box right now, but it's not being natted, and then when it gets to the pfSense box, there's no route back to this inner LAN, so it has no idea where to go. So let's just look at our TCP dump output, ENS on ENS34, let's start out with that one. So I don't think we've worked much with TCP dump yet. It's kind of interesting to think about. So TCP dump just dumps network traffic. Super straightforward. We can say, at the very minimum, we can say absolutely nothing, and it will pick the default interface, and it will just dump all of the traffic that we have on that interface. And there's a whole bunch of stuff going on. And one of the things that we see is we see a bunch of DNS traffic. We see just a bunch of stuff happening on that interface, because there are a bunch of other devices on that interface. And normally when we're doing TCP dump, we're going to want to control what we're seeing a little bit more. But for now, let's say the -I, and then we'll say ENS34, which I believe is our LAN interface. Let me check that again. Yeah, it is 34. And we'll just say ICMP just to control it a little bit more. So I'll have to go back over here and ping 1.1. You can see traffic's coming to our host to be forwarded, but we can see there's no traffic coming back from 2.1, which is Ubuntu 1's secondary interface here, and it's not coming back at all. So let's look really quick at 32, see if any of the traffic is actually coming through from our Ubuntu client up here. So I'm going to have to control it a little bit. Oh yeah, okay. So yeah, we can see actually right here already. We can see the traffic is being routed through our device right now. We can see the source IP address is 2.100, which is Ubuntu client. Or did I change? I don't think I changed it correctly. Now 32 is correct. Okay. So yeah, Ubuntu client still pinging up here. It's just pinging away, not really getting anywhere. And we can see the traffic is actually going through our Ubuntu box right now. But again, hopefully you're familiar with kind of how all the routing stuff works and everything like that. Since it gets to pfSense, the traffic is actually probably getting all the way to pfSense. It gets there and pfSense processes it, and it's like, well, I don't have a route to this 192.168.2 network, so I can't really do anything with it. So yeah, we turn on IP forward. If we hadn't turned on IP forward yet, we wouldn't see it coming through Ubuntu 1 yet. It would come on ENS34, in on ENS34, and it would just sit there, wouldn't do anything. So I'm going to turn off the ping really quick, and then we're going to turn on masquerading. So again, this table isn't visible by default, but we're going to go into post routing, and we're going into our NAT chain. So looking at this diagram again, post routing is the very last thing that happens. So when we're doing all of this, the very last thing that we want to do as we're processing that traffic, as the traffic is moving through us, is we want to change the source IP address and masquerade it. So what we can say is IP tables tnat a post routing what was it, ENS? Let me check here. I got to figure out which interface again. The 32 and 34 is just super annoying, but we have to deal with it anyway. And I'll just explicitly say which interface I want my traffic to be masqueraded through. I want it to be masqueraded through ENS32. That's our main interface. And then I'll say our target is masquerade. If I spelled that right. I'll just clear that out and bring it up one more time. If you couldn't see it at the bottom of the screen there. So post routing, our table is NAT, our output interface is our main LAN interface, so that 1.21, and then we're going to masquerade through that interface. So now that we have all that done, hopefully if everything's configured correctly, when I ping, we are actually getting traffic going through from Ubuntu client to Ubuntu 1 and then going over to our pfSense box. Our pfSense box is responding all the way through. I'm just going to leave that ping on. and let's use TCP dump to figure out exactly what's going on. And I still can't remember the interface names because it's super annoying. 32, 34. Okay, so we'll say TCP dump I ENS 34, I believe. And we can see that when traffic is coming in on 34, it's still exactly the same. It has our source IP address of 2.100, again, our Ubuntu client. It has a destination address of the pfSense box. But then after we go through that host, again, through our routing, through the post routing table, and the NAT chain, masquerading it through, looking at it now, strict that to ICMP. After we masqueraded it, we have an IP address of 1.21, which is our interface address, going to pfSense. And when again it gets to pfSense now, it sees that it came from that 1.21, which is our Ubuntu One's IP address. pfSense knows how to respond to it again, since pfSense has a route to that one network. So yeah, that's kind of an interesting feature of IP tables. Generally speaking, in my mind at least, it's much easier to configure a Linux router. I mean, we took I should say a Linux router than a Windows router, or almost any other type of thing. You can basically take any Ubuntu or any Linux box and change it into a router. So the one thing that I'll go back and I'll look at here a little bit more is actually looking at this OENS32. So one of the implicit features of NAT, of course, is that traffic can only go outbound and you can't get traffic inbound. And we could actually go through and look at IP tables more in advance. And we could actually have inbound kind of port forwarding rules which would allow inbound traffic. But if we weren't specified this output adapter, one of the things that might happen is somebody on our LAN, if they knew our configuration, they could change their default gateway to our IP address here, and they could actually get traffic into our LAN, seemingly. So, if we're not restricting that at all. And it'd be an interesting demonstration, but ultimately just kind of interesting to think about. If we wanted to, let's say, one of the things we could do is, I guess, block specific traffic in our firewall, our super basic firewall. I'm going to just, let's say, 192.168.1.22. So that's one of our Apache boxes. You can see we get a whole bunch of stuff back in response there. I'll just curl something non-existent so we can get the 404 HTML in response. Let's say we wanted to, in our Ubuntu One block traffic to this 1.22 address. What we could say is go in the actual forward chain or table, go in forward, and actually specifically deny traffic to 22. 22, yep. So I could say IP tables A forward. So this would only affect traffic that was going through our box, wouldn't affect traffic from one. And then I could say D192.168, I think it's 1.22, J drop. And now if I was to go back over to my Ubuntu client here, we can see that that curl session doesn't work at all. The traffic that's trying to be routed through is just being dropped instantly. So that's one of the things your firewall might do, is it might configure a bunch of rules in forward, and that's what is probably happening behind the scenes. Again, this diagram right here is very interesting to understand. It's very important for you to see as traffic is going through. If it's going through, it processes through pre, forward, and post. If it's coming in, it just processes pre and in. So you can see here, this is traffic going to the device, this is traffic going through to the device, and this is traffic leaving the device. So just like that. And it kind of is very useful to understand what's going on and what chains are actually being processed and where you should put your rules and everything. I mean, like an instance of that is, let's say we wanted to block to 22. Both traffic going through and traffic going out of our device. One of the things that we might be able to do, we actually can't do this, never mind, we would actually have to add a rule to forward and to output. When we're filtering traffic, dropping it, accepting it, and everything like that, we can only have those rules in filter tables that have the filter capability. And we have filter capability on forward, we have filter capability on output, and you might think, since traffic going through and traffic leaving the device both goes through output, we could just put a rule in this post routing and everything, but we can't do that since that table doesn't have any filter capabilities. There's another example that I have here, and I think I'll just leave it off. One of the things we could also do with IP tables is change where traffic is going to. So let's say we have traffic coming in on port 80 destined for 1.22. We, using IP tables, could actually change where that's pointing to, and we could say, instead of going to 1.22, we could redirect that traffic to 1.21 or something like that, or redirect it to localhost, or redirect it basically wherever we wanted to. And we could do that in a forwarding context, or we could do that in a inbound traffic context. So one of the ways I've used this kind of thing before is I have a service which can change its port, but it can't instruct clients that its port actually changed. So let's say it's listening on port 100 or something like that. I can change that port, for whatever reason, to 120, but clients will still try and connect on port 100. I can use IP tables rule kind of like this in pre-routing to watch for traffic that's coming in on port 100 and internally redirect it to port 120 or whatever port I had configured it to, if I'm dealing with some sort of closed source service that I can't instruct to be nice and play fair, aka VMware, of course. So that's all I have for you today. We're going to think more about this this NAT kind of environment here. I might try and get another vApp provisioned out and sent out to everybody so we can work on this stuff a little bit more. Some things that you've hopefully noted here so far, we have NAT working. It's the very basic things that we need. But we should also probably take a look at DHCP, DNS. Those are other common LAN services that we need. Neither of those are configured right now, and I think we should probably spend some time looking at DHCP and DNS stuff in a Linux environment. So yeah, that's all I have for you today.